All right, so at the top of a new page in your spiral notebook, I want you to title Standard Form of Quadratic Functions. Okay, we're going to start our new unit today, which we're moving from linear to quadratic. We're going to start by talking about the graphs and all three forms of a quadratic, and then eventually move into solving. So what I want to start with for today is talking about standard form, which is written as f of x equals ax squared plus bx plus c. Okay, we're going to end up having three forms, and part of the reason why we have different forms is those forms give us different pieces of information. So let's talk about what standard form tells you. Okay, so the first thing the standard form is going to tell you is this a value, this leading coefficient, okay, is going to determine. Now, before I say this, we need to think about what does the graph of a quadratic function look like. Okay, and hopefully you're remembering that the graph of a quadratic is a parabola. So what this leading coefficient a does is it determines the opening of the parabola. Okay, so you can basically have a parabola that either opens up, which would happen if your a is greater than 0. If your a is positive, your parabola is going to open up. And if the parabola opens up, it might look something like this, okay? Or if the a is less than 0, the parabola opens down. And if the parabola opens down, okay, it might look something like this. All right. So this next thing that the standard form is going to tell you is we talked about the coefficient of a, but the c value right here is also going to tell you, okay, that number is going to be a constant, and that number is going to be the y-intercept. The c is the y-intercept. It's the point where it crosses the y-axis. So sometimes we can get the y-intercept from looking at the graph, but sometimes we can't because maybe it's too high or too low. And so we can just look at the equation and look at that constant and see that the y-intercept is going to be 0, c. All right, so the next thing that's important to know is that parabolas are symmetrical, meaning that we can draw a line and it'll cut the parabola in half, okay? And this line is what's called the axis of symmetry. And the axis of symmetry is always represented by a vertical line, so we would write x equals, and we would put x equals the number, right, that it goes through. And so we can get that axis of symmetry from the coefficients in standard form. And so the formula that we're going to use is going to be x equals the opposite of the b term divided by 2 times the a term. So if we look up here at our standard form, it's the opposite of the b term divided by 2 times the a term, okay? And we get those right there from the equation. And so the last thing that we can get is another important part of a parabola, which is the vertex, okay? So if we come up to our picture right here, the vertex is going to be this turning point in the parabola. It's the point where the parabola goes from going down and then it turns to going back up. We'll talk about that more a little bit later. If the vertex is at the bottom of the parabola, then we would say the vertex is a minimum. But if the vertex is at the top of the parabola, then we would say the vertex is a maximum. So what you're going to notice in both cases, though, is that the axis of symmetry goes right through the vertex. And so the last thing that we can get from our standard form is our vertex, okay? Now, the x-coordinate of the vertex is the same coordinate as that axis of symmetry. So the x-coordinate right here is going to be the opposite of b over 2a. Now, how do we get the y-coordinate of the vertex? Well, what we would do is we would plug the opposite of b over 2a into the function to get the y value. So go ahead and write that down. I know that looks a little confusing at first. So basically what I'm saying is this is the y-coordinate. And we get the y-coordinate, okay? What we would do is we would plug x into f of x to find y, okay? So if you ever want to know what a y-coordinate is, you just plug it back into the function, which is what that means to say f of something. Okay, so let's go ahead and kind of put all of this together so far, and let's take a look at example 1. So for example 1, what we're going to do is we're going to graph the parabola y equal, let's do this. Let's make it function notation. Let's say f of x equals x squared minus 2x minus 3 using 5 points. Okay, here's the kicker, without a calculator. All right, so this is about the time where you're probably moaning and groaning, saying, seriously, we're taking away the calculator. But to really understand the way parabolas work, we need to have a good understanding for how they graph and do a little bit more than just plug them into our y equals. All right, so when I take a look at this parabola, here's what I know. I know that the leading coefficient is 1, which basically tells me, since it's positive, that I can already expect that my parabola is going to open up. I know that the b value is going to be -2, and I know that the constant value, the c, is going to be -3. And what that basically tells me is that the y-intercept is going to be 0, -3, which could help us when we go to do the graphing. Okay. First thing we're going to do is you're going to find the axis of symmetry. And I'm going to put in a little reminder here that the axis of symmetry is x equals opposite the b value divided by 2 times the a value. So let's go ahead and kind of plug this in. All right, so first we're going to do opposite of -2 divided by 2 times the a value. So just to make sure you're kind of following what I'm doing right here, is I'm basically taking, okay, 2 times the -2, I plugged in right here, and I got the a value and plugged that in right there, okay? Now you're probably thinking, all right, if I'm going to write opposite of -2, can we just write +2? And I would say absolutely, okay? There's really no need to write it the way I did. When you take the opposite, you would just make it positive. Now what I do when I graph a parabola is I like to build the graph as I go. And so I'm going to go ahead and take a second, and I'm going to graph right here this axis of symmetry. Okay, we're going to do the best we can. This may not be the best graph in the world, but we're going to do the best we can graphing this without graph paper. And so what we have right here is that the axis of symmetry is x equals 1. Okay, so the next thing we need to do is we need to figure out where the vertex is. And so step number 2, we're going to find the vertex. We already know that the x coordinate of the vertex is somewhere on this line. And so the vertex is going to be 1, and then we're going to plug the 1 into the function, and that's how we're going to get the y value, okay? So what we need to do is we've got this function right here. Now I'm going to recopy it down only because I can't see it at the top of my page, but this is what the given function is. So to find the vertex, we're going to plug the x coordinate of the vertex in. We're going to get 1 squared minus 2 times 1 minus 3. And we're going to keep doing this, okay, just without using a calculator. I'm not going to make the arithmetic too tough. 1 minus 2 is -1 minus 3. And finally, we get the y value is -4. So your vertex is 1, -4. So maybe I come over here and I'm going to graph 1, -4. Okay. So now what we need to do is for step 3, you need to graph 4 additional points. Now that sounds like kind of a lot, but I think you're going to see that this is really going to be pretty easy. So I'm going to come back up here to the given information, and I'm going to highlight right here the fact that we identified that our y-intercept was equal to 0, -3. So this is really going to be an easy point for us to graph, that if I plot my y-intercept, oops, let me do this in pen. If I do my y-intercept at -3, that then I can reflect that point over the axis of symmetry. And in fact, I now get 2 points right here, okay? So now, just like that, we already have 3 out of the 5 points. So we just need 1 more point to graph, and then we can reflect that over. So let's stick to points that are close to our vertex. We already have this point graphed, we have this point graphed. So now we've got x equals 3. We could also plug in -1. Well, if we had to take a pick between the two, I'd probably pick the +3 just because it's easier to plug in a +3, okay? So let's go ahead and plug into our function +3 squared minus 2 times 3 minus 3, okay? And let's do that arithmetic. 9 minus 6 minus 3. So this is going to be 3 minus 3. And finally here, we get that this coordinate is equal to 0. So we just found that the point 3, 0 is on the graph. And so I get 3, 0, okay? Now, let's reflect that point over. This point is 2 units from the axis of symmetry. So on the other side of the axis of symmetry, we can graph this point right over here, okay? So here's our parabola. And so really, to tell you the truth, it's not too tough to graph this parabola with 5 points, because a lot of times really we just basically graph 2 points and then reflect them over the axis of symmetry. So here's what we're going to do next, okay? What we need to start talking about are attributes of this parabola. Now, I'm going to label this section in your notes, attributes of a parabola. And what I need to do first, and I apologize for being a smidgen redundant, but I don't have a lot of choice here on the iPad because I can't just show you that same picture. We just need to take a second. I want to take the picture that we just graphed and I'm going to kind of recreate this. So if you could just take a minute with me here. Okay, I'm just going to regraph this. Honestly, if you don't want to regraph it, you can probably just use the graph that you have above, but this is what we have so far for our parabola. Okay, and so I'm going to go ahead and graph this, and these are the things, oops, not quite sure about that line. This is what we're going to talk about when we talk about the attributes, okay? So this is what we're going to write down. We're going to locate the vertex. We're going to locate the axis of symmetry. We're going to locate the roots. We're going to locate the y-intercept. We're going to talk about the domain and the range. And then we're going to talk about here the intervals of increasing, the intervals of decreasing, and then finally, this last piece should be kind of new. We're going to talk about the end behavior of the graph. So you can go ahead and kind of look over this and, kind of decide what you've seen before and what you haven't. Some pieces are going to be easy because we've already talked about them here. So we've already located the vertex. We know that the vertex is 1, -4. We always write the vertex as an ordered pair. Your axis of symmetry is this green line right here. It's a vertical line. And so when we locate the axis of symmetry, we want to make sure that we write it as a vertical line and we write x equals 1. You will lose credit if you just put 1 on the blank. It's got to be written as a vertical line. All right, the roots of the graph. The roots are another word for the x-intercepts, okay? Later on in another unit, I'll eventually call these the zeros, which is another word, but the roots are your x-intercepts. And so the roots are going to be written as an ordered pair, and we can write these as -1, 0, and I can write this as 3, 0, okay? The y-intercept is written as an ordered pair, and it's 0, -3. So all of those parts really we talked about before. Let's get into the domain. So what the domain is the domain is the vertical span of the graph. It's your set of input values is another way to think of it, okay? So basically the domain are all of the numbers that we can plug into the function, which really you can plug any number you want into a quadratic function. And so what we're going to say is the domain is -∞ to infinity. Let's maybe look at a little bit more of a visual approach. Okay, for the domain, this parabola goes forever to the right and the parabola goes forever to the left. And so when we look visually at domain, what we're really looking at is the horizontal span. And this parabola, even though it's really steep, it's really going on forever to the right, forever to the left. So the domain of a parabola, unless I give you a parabola that maybe looks like this that has endpoints, the domain of a parabola is always going to be -∞ to infinity. Now the range is a little bit different, okay? The range of a parabola is going to be the set of all output values, okay? And what we see here, it's going to end up being the vertical span of the graph. Well, the lowest point on the parabola right here is going to be at -4, but then we can see that the span of it goes up forever. And so the range is the vertical span of the graph. And we would say that the vertical span is going to go from -4 to infinity. All right, so the next part I want to talk about, which may or may not be new, is the intervals of increasing and decreasing. So what I want you to do is I want you to put your pencil on the part of the parabola where the parabola is going up. Okay, what do you think that means? If I say put your pencil on the part of the parabola where the parabola is going up, well, I would put my pencil over on this part. Okay, this part of the parabola, so down at the vertex is the lowest point, but right here the parabola is going up. Now put your pencil on the part of the parabola where the parabola is going down, and that would be over here, and it's decreasing. So the way that we're going to write this is, okay, is we're going to basically split the parabola in half, and it splits in half at the number 1. Okay, so I'm going to kind of make this a number 1 right here so you can see. And so the axis of symmetry really splits your parabola into a right half that goes forever to infinity, and it divides the parabola into a left half that goes forever to negative infinity. So when we talk about increasing, decreasing, I don't want you to talk about it in terms of the y-coordinates. I want you to talk about it as meaning on the left of the axis of symmetry or on the right of the axis of symmetry. Well, on the left side of the axis of symmetry, your function decreases because all these y values are getting lower and lower and lower. Then you hit the vertex, and then on the right side of the parabola, all these y values get bigger and bigger and bigger. Okay? So that's kind of the idea there with your increasing and decreasing. So how do we write this as an interval? Okay, so what we're going to do is we are going to write the interval of increasing is going to be from 1 to infinity. Now I'm going to use a bracket here, okay? And I understand that it would maybe be more intuitive to use a parenthesis, but basically what has been decided is that starting at the number 1 going to infinity, this function is increasing. Now on the other side, okay, the function is decreasing. And so we would say that it decreases from negative infinity to 1. But again, I use a bracket because what has been determined is that it decreases all the way to exactly 1. So it's almost like we're saying that at the point 1, the function is both increasing and decreasing, okay? And that's kind of the big mathematical argument is whether you use a parenthesis or bracket. But the latest thing has been determined that we use a bracket. So the last thing is going to be end behavior. And what we do for end behavior is we're basically going to describe what the ends of the graph are doing. And so really the best way to kind of describe this is we're going to write this as x goes to infinity. Okay, and what we're going to do is we're going to describe what the f of x values are doing. So let's just talk about that notation for a second. When I make this arrow basically means approaches. Because what we need to understand about the graph is that in your parabola, we can graph the point 4, okay? But we could also come all the way out here to the parabola and we could graph the point 100. We could graph the point 1,000,000. This graph, okay, your x values, because the domain is negative infinity to infinity, your x values are going to go forever to the right. Well, the question is, what are the y values doing as your x's get bigger and bigger and bigger? Well, if you look right here, your y values are continuing to get bigger and bigger and bigger. So what we do is we say that the y values, which is really your f of x values, your function values, are going to infinity. Now, the part that I'm doing in blue, this is what we do every single time. Okay, so this is almost like the template. We just more need to get used to the notation than necessarily understanding what this end behavior is. Now, what I'm saying is as x gets smaller and smaller and smaller. So we could keep going out here and graph all the way to negative 100 or negative 1,000,000. Well, all the way out here when we look at the y values, okay, what are the y values doing? Your y values are also continuing to get bigger and bigger and bigger. And so what we say is that it goes to infinity. So what we're doing when we do the end behavior is we're basically saying that on the right side of the graph that the y values go up forever, but on the left side of the graph your y values are also going up forever. Now, what makes end behavior a little bit easier with the parabola is the parabola is either going to both go up forever, or if it opens down, they'll both go down forever. So it's going to stay pretty simple. End behavior is one of those things, honestly, that we're going to keep talking about with every function, and that'll get a little bit easier as we go. All right, so let's wrap this up with our last example, okay? This is something that I usually kind of throw into the homework and students have trouble with it. So let's just look at a question like this, and let's kind of see how we would walk through something like this. Y equals ax squared plus bx plus 3. So let's suppose I'm given this equation in standard form. For what values of a and b will the vertex be -4, -5? Okay? So we're going to kind of use what we've talked about and go backwards and figure out what the coefficients a and b must be so that our vertex is -4, -5. Okay, so when we start something like this, go ahead and hit pause if you need to, if you want to write it down. But then let's go ahead and hit play when you're ready. All right, so we need to think about maybe what we know about the coefficients of a, b, and c and how that affects the vertex. Well, the first thing that we know is your axis of symmetry. Okay, the axis of symmetry is going to be x equals -4. Okay, so how do we get the axis of symmetry? Well, the axis of symmetry is what you get when you take the opposite of the v value and you divide by 2 times the a value, and we know that that's going to equal -4. So maybe we work with this a little bit. Maybe we multiply both sides by 2a. Well, if we multiply both sides by 2a, I have -b equals this multiplied, which is -8a. Okay, maybe we divide by -1 and we get b equals 8a. Now we're done solving right there. All right, I can't get a or b equals because I have too many variables. So let's think about something else that we know about this vertex. Here's the other thing we know. When x equals -4, okay, then when we plug -4 into all of the x's in the equation, all right, that we know that y is going to equal -5. So let's start with this function right here, ax squared plus bx plus 3, and let's replace the y, okay, with -5, and let's replace the x right here with -4. And let's go ahead and see how this is going to work. And so this is also going to be -4 when I plug this in. Let's do the arithmetic and see what happens here. So -5 equals positive 16a, right? Whenever you square a negative, minus 4b plus 3. Okay, well, let's keep simplifying. Maybe I minus 3 from both sides. -8 equals 16a minus 4b. Well, now what I have is I basically have a system of equations. I have b equals 8a, and I have this equation, -8 equals 16a minus 4b, and I can use substitution and elimination. Well, since I already have the b that's solved for, I think what we could do pretty easily is we could substitute the 8a into this b. So let's see what this is going to look like. We come down here, I'm going to say -8 equals 16a minus 4, but let's replace the b right here and let's substitute in 8a. So now, using those two pieces of information, now I have an equation written as a single variable. 16a minus 32a, -8 equals -16a, divide both sides by -16, and we get that 1/2 is equal to a. So when we can just plug that back in. So if b is equal to 8a, then that means that b equals 8, and I can substitute in the 1/2 from what I found. So we've got that b is equal to 8 times 1/2, which is 4. And so what we just found is that the a would be 1/2 and the b would equal 4. and that would be the answer. So what I'm really doing is I'm saying that the quadratic function that is y equals 1/2 x squared plus 4x plus 3, right? If I come back up to the beginning and I substitute in for a and for b, I basically just kind of found the function. So this is your answer right here, but if I had a question like this on a test, maybe what I would do is I could plug in my a and my b, put this in your calculator, and see if the vertex is equal to the given vertex, -4, -5. All right, just a little strategy there that you could use to check your work. All right, so that's it for now. We'll keep working in class, and we'll see you next time. Bye.